Hi, welcome. In today's video, I'll keep working on the examples covered in the last video. Still considering the ket plus as the used quantum state and the operators as x, as y, and as z. What are the uncertainties associated to measurements of Sx, Sy, and Sz on the ket plus? So to answer that question, we gotta look to the uncertainty definition. For a given operator A, the uncertainty is defined as delta A equals square root of mean of the square minus the square of the mean. In terms of expectation value, the first term can be seen as the expectation value of the operator A squared, and the second term can be seen as the expectation value squared. These two terms are not always the same, and we need to distinguish them. I'll start from the simplest case, Sz, then the uncertainty associated to this operator, considering the ket plus, is defined as the second term right here. We have already calculated, and we just need to square it. The expectation value of Sz, considering the quantum state ket plus, is h bar over 2. Then this term squared is h bar squared over 4. Basically now we have to calculate the first term of this expression, which will be Sz squared, by definition seen before, Bra plus Sz. I can split this Sz squared as Sz times Sz ket plus. And I know what happens when the operator Sz acts upon the ket plus. It gives us plus h bar over 2 ket plus. Then I write it down, plus h bar over 2 ket plus. I can take this h bar over 2 out of these brackets, then h bar over 2 bra plus Sz ket plus. If you react this operator upon this ket again, we have the same result, bra plus plus h bar over 2 ket plus. I can take it out and have h bar squared over 4 ket plus, bra plus ket plus. It must be equal to 1. Then we have here h bar squared over 4. Then if we plug back the value for the first term and the value for the second term, we end up with the uncertainty of associated to a measurement of Sz on the ket plus is given by square root of h bar squared over 4 minus h bar squared over 4. It's equal to 0. Well, this result is expected because there is only one possible result, hence there is no spread in the results of the measurement. We can sketch a histogram for this case, and it will be something like this. The vertical axis will be the probability, the horizontal axis will be our operator. Then for the case of ket plus, we have 100% probability of get h bar plus h bar over 2. We are here considering the quantum state ket plus, where the expectation value of Sz is h bar over 2. Therefore, the uncertainty associated to a measurement of Sz on the ket plus is equal to 0. And you can see here the probability of find spin down is 0, and the probability of find spin up is equal to 1. This is the histogram that illustrates the case of the operator Sz. Similarly for Sx, the uncertainty is defined as we calculated in the previous video. This part here, the second part, expectation value of the operator Sx was found to be 0. Then if we square that, it's still 0. The first term we can calculate now. I'll do it like in a faster way. This result again makes sense because each measurement deviates from the expectation value 0 times h bar, let's put that way, but the same value of h bar over 2. I'll draw the histogram for this case in the next page. For ket plus, the expectation value of the operator Sx is 0, and the uncertainty associated to this measurement is h bar over 2. Then the histogram will be something like through this histogram we can confirm what we found before in the previous video, the expectation value, because there are two possibilities. For the measurement we can get minus h bar over 2 and plus h bar over 2. Therefore, the expectation value is 0 because the average between these two values, plus and minus h bar over 2. And at the same time, the uncertainty is plus h bar over 2, which makes sense because each measurement deviates from the expectation value. I mean, deviate from the orange by the same amount, which is plus h bar over 2 and plus h bar over 2. Then makes sense that our result is spread in this value h bar over 2 as found by the uncertainty. Finally, for the operator Sy, the uncertainty will be calculated as we did before, and the expression for the uncertainty is given by this one. So we already know from previous result that the expectation value of the operator Sy, taking account the quantum state ket plus, is 0. If we square that, it keeps being 0. Then we just need to calculate the first term. I'll leave this as exercise, but if you do it, you'll find exactly what we found for the Sx case. H bar squared over 4. Just to remember to write the ket plus in the SY basis, which is given by this expression here. And then you follow all the steps I've taken in the previous example, and you end up in the right answer. And if you plug all these values back to this equation, we will find the uncertainty for SY. Once again, this result makes sense for the same reasons given for SX. I'll write down now the histogram for this case. It will be like in summary, for ket plus we have the following. It's all for this video. Thanks for watching. See you next time.